So let me see how this works first. Well, while I was preparing the presentation, I was told that I was going to be talking to a group of Picosat experts, which I'm not. I'm a propulsion expert. So I prepared a little quiz for you. It's just one question, so if you could take out your phone and scan the QR code, please. So while you scan it, I have to say that the numbers in there are the number of satellites are from the NanoSats EU from last year, so probably there are more satellites launched. And the number of missions are the ones that I've been able to find. So, whoops, maybe that side. Oopsie, that one. So that's the question that you'd be answering, and it's out of the approximately 200 Picosats that have been launched up to date, how many do carry propulsion on board? I'm going to give you like 5 seconds, although I've seen that most of you have already answered. Okay. So the correct answer, or at least the ones that I've been able to find, is 5. Congrats to every one of you that got it right. And we basically found this a problem. So the fact that only 5 out of 200, approximate numbers again, only have propulsion on board is really a problem for us. So we think that there's a lack of availability of onboard propulsion. And that is what we're trying to solve. We're trying to do better propulsion. That's what we're building at Ienai Space. My name is Gema Arboleya, as I already, well, Gema in Spanish, Gema in English, depending on your nationality. And I'm a business engineer for Ienai Space. So this is kind of our team. This is the amazing team that's behind all the work that I'm going to show. We're currently 13, and we just opened 3 more positions, but for you to know everyone. And our vision is basically that we know that in-space mobility today is an industry demand for anyone that wants to have a professional service. So this is because of, in the first place, positioning yourself in orbit. So I know that there are other techniques, such as differential drag. You can have different masses and stuff, but that gives you much less control authority than, of course, carrying a propulsion system on board. Then we have the station keeping. That is especially critical for Picosats because of what someone already mentioned, the mass to drag ratio. Sorry. So basically, this is a case study that we did last year, and shows that when carrying propulsion on board, you could actually double the lifetime of your satellite. So it is quite a critical thing if you were thinking of reducing time and costs of the mission, and especially if you're deploying a constellation. Now, the last thing is something that has already come up at some points, which are the infrastructure protection. So in this, you have 2 sides. On one hand, the FAA released a regulation, I think that was kind of a month ago, about the deorbiting, that you need to do it 5 years after the end of your mission. So that if you're flying really, really low may not be a problem, but what is a problem is the space debris. So there are 236 constellations planned for LEO, only within the new space industry. And not only that, but there's already space debris out there. I read this the other day, and it's that Starlink satellites have performed just in the first half of 2021, 2,219 collision avoidance maneuvers. So LEO and space in general is actually becoming really crowded. Therefore, having propulsion is something key. So if it's such a key feature, why don't Picosats have more propulsion? Well, the main factor that we have identified as a problem is the platform constraints. When it comes to Picosats, you have on one hand the volume. So the volume only allows us to put inside basically electric propulsion, because if you go to chemical, for example, it may be a bit bigger, so you don't have much volume. And the next problem is the power available. So the thing is that electric propulsion needs to be efficient for it to be useful when you use it within a Picosat. Now, I'm not going to show you another QR code, but I do want you to try to link the types of propulsion with the efficiencies and the powers that you have there. I'm going to give you 5 seconds, some kind of. And I'm sorry beforehand because I was only able to find the 1U form factor. So those are the correct answers. I hope you could match some of them. But what I want you to focus on in here is the efficiency and the powers at which you reach that efficiency. So there's not a single, let's say, propulsion system among those ones that has an efficiency higher than 15%. And the minimum power that you have is 8 watts. So is there high efficiency possible at lower powers? It is with what we call the next generation propulsion, which is electrospray. I don't know if you are familiarized with it, but basically the way it works is you have an ionic liquid or a molten salt inside a tank. That flows passively towards a component that we usually call the emitter. Then we generate a voltage difference between the emitter and the grid or the extractor, and that generates an electric field that is concentrated at the tip. Now we're able to accelerate the flow of up to, I think that it's between 30 and 50 kilometers per second. And it's a really, really efficient system. In our case, or next generation propulsion ATHENA, is called ATHENA. Now you have in there the CAD version of both the CubeSat and the Picosat. I've heard the word modular a lot also today. So one of the features of ATHENA is that it's modular. So you tell us how much space you have, and we cover as much as you need. In the case of the Picosats, that you don't really have much margin, that is the version that we've built. And it's approximately 50 by 50 by 25, I think, right now. And those are the specs of our latest test campaign. So the lowest power that we can reach for now is 3 watts. We give you the thruster power just to make up your own numbers, because we know that it may depend on the manufacturer and stuff. Specific impulse is between 1,600 and 2,000, and the efficiency for a Picosat. So if you go up to CubeSat, it would increase. But for now, it's for 20 to 30%. Now, I would like to remark that this is just the engineering model that we currently have. So we are expecting to increase this even more when we go to the commercial product. And for you to see that it's not only a render, I brought this little one. That is the one that we flied in the Genesis mission with some friends' company from startup that is Hydra. I think that they will present tomorrow, and I'm sure it will be a really interesting presentation. So, whoops. For this one, that was our first engineering model prototype. We tested it and built it in-house. The picture on the left is in our vacuum chamber. If you run it at a bit of a higher pressure than the one that you should, if not, you cannot really see our technology. Then we passed all the qualifications, so that includes the thermal vacuum and the vibrations test. And we integrated it in a 1.5P. And then to the black. So I think that someone already mentioned Firefly. We were also on that flight. Sadly, we were left a bit below the orbit that we should have. So the mission was quite short, only 4 days, and we weren't able to retrieve any other data. But that's why we have another flight planned for the end of 2023. So I've talked about propulsion, but how do we leverage both our software and hardware to give you better propulsion? Well, what we provide is an end-to-end service. So we do not only just give you the thruster and there you go, but we try to go with you throughout the entire process so that we can tailor the thruster to your mission. And this way you won't have a centimeter more of space, not a gram more of propellant, or anything else. So this is kind of our life cycle product go through. The first one is Go. It's an open access tool, so you can access it through our website. It's a preliminary mission analysis design, and it's just for you to play around and see your capabilities, see what you could improve in your mission by adding our thruster. Then we have 360, which is an in-depth mission analysis tool. So with this one, basically, what we do is we define with high fidelity the propulsion requirements of a mission. Then we can also perform concurrent engineering between the propulsion system and the other subsystems of the satellite. And finally, we can, of course, simulate the propulsion maneuvers during the conceptual operations. So this way, again, what we try to do is we try to tailor the thruster to the specific mission of our clients. Now, once it's optimized, we don't just give you the thruster and operate it, but we're currently developing Orbital, which is to support the client throughout the mission. So with that, Orbital is basically a near real lifetime maneuver optimizer, because we've seen that missions not always go as planned. Oops. So this is a 360 case study for you to understand why we think that it's key to actually take into account the propulsion system with the rest of your mission. It was done a year ago, so we have improved slightly, I think a lot, actually, your capabilities, but it's just for you to have a taste. So in this case, the requirements were we had a 4p Picosat. We could only fire during a 20% of the life cycle and only during sunlight. The worst case analysis approach was taken for everything, so let's say the solar cycle and everything like that. And we considered a 2U drag area. The mission requirements were the in-plane facing and the station keeping. So as for the in-plane facing, we analyzed two cases, the 90 degrees and the 180 degrees. The 180 degrees was the worst case scenario that we could look at. So in that one, you can see that the curves that we obtained are Pareto front, in which you can see the amount of propellant and the days that it takes you to reach your desired position. And we have the two, let's say, extreme solutions are the fastest one, in which you use 1 gram of propellant, but you reach the desired position in less than 12 days. And the other one is in which you use less than 0.25 of propellant, but you take more than 30 days. So if you have very few time, it's actually a critical thing to take into account. But as you can see, you can basically choose your desired point. Now, once you reach the in-phase, now you reach your desired position, what we did was station keeping. So for this case, we took into account a 10-kilometer margin within the 500-kilometer semi-major axis. We, of course, maintained the in-plane facing constraint, and we also included the inclination. So as you can see in the picture of the left top, your right, sorry. Basically, you go down to the lower limit and we fire, we go down to the lower limit and we fire, and all the way around. And then in this one, you can see that we fire only during sunlight and with the 20% duty cycle. So basically, the final study was that you would need less than 2 grams per year, and you would need to fire between 4 and 5 days consecutively, each between 2 to 3 months. The outcome of that was that when using our propulsion system ATHENA, with those requirements, you would need 4 thrust hits, and those are basically the numbers that we obtained for this specific mission. But again, what 360 is used for is just to understand your propulsion requirements. So it doesn't necessarily need to fit 4 thruster heads or ATHENA. Like we just want you to understand what you need as for the propulsion system. So what I would like you to take out of this is that onboard propulsion is necessary. It's not, propulsion for Picosats is feasible, so you can do it, and it's not only feasible, but the electric propulsion can sometimes be the optimal or the only solution. We really ask you to understand your propulsion requirements beforehand, and we think that performing concurrent engineering is key, and taking propulsion into account at the beginning of your mission is key for that. And yeah, I think that those are our main points. But before finishing, I have another QR for you, which is you have a really, really important mission. So as I mentioned, we're a Spanish startup. We just started 3 years ago. We have the Picosat model, like engineering model, but we don't have a commercial product yet. So what I'm doing here basically is trying to understand the propulsion requirements. I'm trying to understand if you guys that are experts in Picosats basically think that you need propulsion. And if you need propulsion, for what do you need it? And if you would pay for it. So if you could please take up like 5 minutes to fill up the survey, that would be amazing. Thank you. Oops. ¿Qué me pasa?
Do we have any questions? Are we... Got one question here.
I don't know if you have already mentioned this number, but for how long this system can be working in orbit?
It basically depends on the amount of propellant that you want to carry. So the way we usually work is you tell us your mission requirements. We do the simulation with 360. And we tell you the amount of propellant, the size, and everything that you would need to carry to fulfill those mission requirements. Now, if you cannot have that volume, that, of course, can be an iterative process, and that's why we think that's so important to try to take into account the propulsion system at the beginning.
So the design can be modular?
Yeah, it's modular, as someone else has said before.
propulsion in a single mission, I suppose it's basic, basic chemical and...
Chemical and no, not yet. We have thought about it, but we're still focusing on the electrical propulsion part.
Any more questions? Joe?
Always the thing with hockey teams, price.
Yeah.
What is your price range that you're looking at?
So if you've looked at the survey, this is one of the questions that we ask. How much do you think that carrying propulsion on board increases the let's say, helps the mission? So at least what we try to do for CubeSats, so that's the standard I'm going to give you, is we are trying to bring down the historical cost of a 25% to between 10 and 15. And for Picosats, we are currently looking into the market. So that's why it's important for us to know if you would pay for it, and if you would pay, how much would you pay? Like, how much is it worth? Because maybe from some point onwards, it's just not worth for you. So that's also what we like to understand.
Awesome. I think that's everything just now. So big round of applause.